In the previous lecture video, we talked about the definition of the Taylor-Maclaurin series, and I'll just remind you, we found that the Taylor series for a function centered at a point x0 is given by this. So it's t of x. This is a Taylor series. It's a series, right? Power series. It's a sum and goes from 0 to infinity of the derivatives of this function evaluated at x0 divided by n factorial. These are the coefficients of the power series times the power series terms, x minus x0 to the power n. And we said that there's a very special Taylor series that gets another name. So I like to always call it the Taylor-Maclaurin series, but most books just call it the Maclaurin series until you get a little further on and people start putting Taylor back in there. But this is just given by, this is the special case when x0, the center point, is the origin. So it's equal to 0. And we'll still call it t here, but this is the sum, n equals 0 to infinity of f and nth derivative at the origin now over n factorial times x to the power n. So the only difference here, these are really not different, right? The only difference here is that we've made this special choice of x0 equal to the origin. So for the Maclaurin series, you can just say Maclaurin, and that if you see this word, right, Maclaurin, then you know that the center point is the origin at x0 equals 0. Okay, so now that we've reviewed that, in this video we would like to find a formula for the Maclaurin series, or the Taylor-Maclaurin series of the function f of x equals e to the x, okay? So we want to find the Maclaurin series. That means that we need to work out a formula for the nth derivative here, right? So we will know the Taylor series, or really any series. We will know the series if we know the coefficients. So I'm just going to rewrite this like this. All right, C sub n, this is our job. If we can identify these coefficients, we will know the series. And we know that for this Taylor series, or the Taylor-Maclaurin series, the coefficients are given by this formula. Okay, so C sub n is the nth derivative at 0 over n factorial. All right, well, the best way I think to work this out is to actually make a table. I'll do it over here so we can see what's going on here. Let's just make a table. Let's list out some n's here. We just need enough that we see a pattern. I started here with n. I want a general form, right? So I'm going to put n down here as part of the table as well. And then we need a table for the fn formula, function evaluate, so the nth derivative of the function as a function of x. So usually we need to always be very clear here that this is the derivative as a function, and then we'll plug in our center point and get our c sub n out of this. So this is going to be, remember, the value of the derivative evaluated here divided by n factorial. So let's start plugging into this list. If you don't take any derivatives, the zeroth derivative of a function, that's just the function itself, right? And remember, the function that we're trying to find the Maclaurin or Taylor-Maclaurin series for is e to the x. All right, what I like to do is just take a bunch of derivatives here and then notice a pattern, and then we can plug in over here to the coefficients. So let's just do it, right? But think about this function. This was a really interesting choice because this function, its derivative is itself, right? It's a remarkable function. It's not 0 ever, but it is equal to its own derivative, right? And so we really just have to fill out this list with a whole bunch of e to the x's because the derivative, I'm taking derivatives here even though it doesn't look like it, right? The derivative is always just equal to the function e to the x itself. And now it's easy to plug in because remember, x0 for a Maclaurin series is 0. So what I'm doing here is I'm evaluating e to the 0, and dividing by n factorial, right? So the first term is e to the 0, which is 1, over 0 factorial. The next term is e to the 0, which is 1, over 1 factorial. Notice the n, right, plays a role here. There's a factorial, 1 factorial. The next one is 1 over 2 factorial, 1 over 3 factorial. And we can see, we don't even need to write the 4, right? We see the pattern. The general coefficient is going to be 1 over n factorial. Okay? So what we have to do now, this is it, right? This is the goal. This right here, this lower right-hand corner of my table, that's the goal. Because like I said, if we know the coefficient, we can just plug it in and we've got our Taylor series. The other thing that we know is that this is 0, right? The center point, because we're talking about a Maclaurin series. So what we've learned then is that the Taylor series for e to the x is equal to the sum, and goes from 0 to infinity, of, plug in our coefficient, 1 over n factorial times the power series term, so times x to the n. And just for the sake of understanding what this looks like, let's write out the first few terms of this. So this is 1 over 0 factorial x to the 0. Remember, 0 factorial is 1, right? It's 1. So this is 1 plus 1 over 1, 1 over 1 factorial times x, plus the next one's going to be 1 half x squared, and then 1/6, 3 factorial is 6, x cubed, and then 1 over 24, x to the 4th, and 5 factorial is already 120, and then 6 factorial is 720, and they just keep getting bigger denominators from there. And it turns out that this is the Taylor series for e to the x, the Maclaurin series for e to the x. And a question that we have not yet answered in the notes is, how can we be sure that this series actually equals the function? We'll talk about that very soon. But it turns out that this does truly equal e to the x, and it turns out that it equals e to the x for all x, so for all real numbers. And like I said, we'll show that very soon in the notes. For now, you just believe it, but this is true for all x. And what this does then is give us one more way to represent the number e. So the number e we've defined in calculus courses a number of different ways, but here's another way, right? So the number e is just e to the power 1. Well, e to the 1 is going to be equal to, if we believe this, right, it's going to be equal to replacing all these x's with 1s over here. And so e is equal to the series, n equals 0 to infinity, the sum of the series, 1 over n factorial, times 1 to the n, right? So this is just 1 plus a half plus a sixth plus 1/24th plus 1/120th plus 1/720th, etc. And so that the sum of this infinite series equals the number e.